Hello, welcome again to electrostatic fields. Today we have the divergence theorem and the first Maxwell equation. So let's have a fast recap about Gauss's law for electricity. And we concluded that the electric flux equal to the enclosed charge. And we give two examples, even there is charge in the medium, but our surface doesn't include any charge. So our phi E is equal to 0. And if we have another surface like this one, but it includes some charges, positive charge and negative charge, and we conclude that phi E is equal to Q positive minus Q negative. So now we are with the divergence theorem, which states that the flux of a vector through a closed surface is equal to the volume integral of the divergence over the region. So if we calculate the flux, it can be calculated using the flux density, just double integral over a closed surface, for example. Our theorem states that if you took divergence of this vector, you can calculate again the flux if you integrate over the volume caused by this surface. In summary, double integral of some vector f dot n ds is equal to triple integral of the divergence of this vector the volume. And here we can another way to say divergence we call nabla dot f dot product here. And very important to note that it should be a closed surface. This can be a spherical shell, it can be a torus, and also it can be a cuboid, but it cannot be either of these, just a 2D surface like this, or even a hemisphere. This also is not acceptable. Now we care more about the electric flux density. This is what we have studied, which is D. So we know that electric flux equal to double integral of the electric flux density dot nds. We can benefit from the Gauss theorem. We can say triple integral of the divergence of the d volume. Let's have the second point of discussion here, which is the Maxwell first equation. And in the integral form, we start from the Faraday's law for electricity. We have the flux equal to the enclosed charge. We can rewrite the flux as a double integral over a cross surface d and ds. Then we can say enclosed also is calculated by the charge density over volume, and we triple integrate this over the volume. Equating these two things together, we can get the first Maxwell equation in the integral form here. Another form is the differential form, and which we can get by applying what we have just studied, the divergence theorem. Apply the divergence theorem on the flux. You can get here, sorry, this one. So this is just what we have in the previous slide. Double integral d dot n ds equal to triple integral divergence d volume. Then we equate the two quantities, this quantity here and this quantity. If we equate together, then we have a triple integral here, the volume, and a triple integral the volume. This means that what is inside here is equal to what is inside here. And just we have derived the first Maxwell equation in the differential form. Divergence D equal to rho v, or nabla dot D equal to rho v. The diversion is a vector calculus term which is applied to vectors, and the result will be scalar. Just we have input as a vector field, we have output as a scalar field, and divergence something in the middle. It comes from the multiplication of your vector with nabla. So once you know your coordinate system, either Cartesian, cylindrical, or spherical, this is how it looks like in Cartesian with your input this vector. This is how it looks like in cylindrical coordinates when you have your vector looks like this. And finally, in spherical coordinates, it will look like this when your vector or input vector is like this. Another thing which we care about is the infinitesimal length, which appear to us, for example, what is ds and what is d volume, and we will use later also. So let's have example one to apply what we have learned in this video. We are given a flux density d as a component of phi, I mean direction of phi, and the magnitude of this is just 20 over rho multiplied by cosine phi over 2. And we also are given where is this valid. We are in terms of rho, it's from 1 to e. In terms of phi, it is from 0 to pi, and in terms of z, it is just between 0 and 2.5. And the question is determine the total charge lying within the region. We have the direct method. We know that phi e equal to q enclosed. This is what we know. So the two ways to calculate q enclosed are simply the two ways to calculate phi e, which are the two sides of the divergence theorem. To solve this problem or this kind of problems in general, the most important thing is to identify the area and the surface where we do our calculations. So we are given that we our rho is bounded from 1 and e, our phi is bounded from 0 to pi, and our z is bounded from 0 to 2.5. So assume this one is z0. This point here is z equal to 2.5. We have an inner radius here, which is 1, an outer radius of e, and phi is bounded from 0 to 180. So this means this is our x-axis, and if you go here, you'll find this minus z-axis, which is phi equal to 90. So here we have phi equal to 0. Sorry, phi equal to pi here. Now we have drawn the surface itself. We need to care what we are given here. We are given phi component only. We don't have either z component or a rho component. So surfaces where rho is perpendicular, we don't care about, but because at the end we are calculating um, d dot n ds, so n is our perpendicular or our normal vector. So if the normal was rho, we don't care. If the normal was k, for example, this upper surface here, this we don't care about because normal is k. Below we have a similar surface here, we don't care. The cylindrical surface here, this one normal here is rho, so we don't care. So finally we have only two surfaces. Let's draw it from above. This draw again from above. So this surface here we have phi, and other surface here we have phi as perpendicular. So this is the two surfaces where we do care to calculate our flux. Once we identify the surface, everything will be easy. So just calculate what is d at this specific surfaces. So our n here, as we can see, phi is negative, and of course also here phi will be negative, and value of phi at this specific point is 0. So we will apply this to our d equation. Once you apply this, you give you cosine 0, which is just 1, and then you are left with 20 over rho in the direction of phi. Then we apply the equation, this equation, substitute here. Then you will get a minus phi multiplied by phi. This dot product will result in 1, but of course not forget about the negative sign. Then simple calculation for the two integrals. One integral for rho from 1 to e, and one integral for z from 0 to 0.5. So we divide the two derivative here. So we divide the two integrals. Then it's just very simple mathematical calculation. One will bring you a ln, and one will bring you just z, and substitute here and calculate the two equations, resulting equations, and then you just get z component will be 2.5, and the rho component will reduce to 20, and add this together. Then you will get phi e at this specific surface, which is phi equal to 0, this one here, equal to minus 50. Do this again at the other surface. The difference is that you will substitute with phi equal to pi. You still have the same thing. Phi is equal to, sorry, n is equal to minus phi. Then go ahead, substitute. The good thing here that your d is equal to 0 because you got cosine pi over 2. So simply the remaining will phi equal to 0. And finally, you add everything together, which you will at the end you have here 0 and you have here minus 50. So total will be q enclosed is equal to minus 50. So to do the other way, just use the divergence. I bring the divergence here for your memory. Applying this one, you don't have a rho component. This will be 0. You don't have a z component. This will be 0. Then you just use this term here, substitute with the value which we are given. Then do the derivative. 20 over rho is not a function here, so get it outside. And just take the derivative of cosine phi over 2, which is minus 1 over 2 sine phi over 2. Simplify, you get minus 10 over rho squared multiplied by sine phi over 2. Then the good thing here, you don't care about the surface itself, just use the boundaries which are given. Directly substitute in the integral or the volume integral. You will get this integral divided to 3 simple integrals. Once you do so, you just need to solve each integral. One integral bring you to zero point 0.5 in terms of z here. When you integrate for phi, just remember we only are given up to pi, from 0 to pi. Then do the integration of sine, bring you minus cosine, but don't forget what is inside here. It just get flipped. And just substitute with the boundaries. Then at the end you get all of this brings you to, and do the same for rho. Here you got a len. Here we have len e, which is equal to 1. This go 1, this one goes 0. Then just what is outside is 10. Just multiply, you get here 10. Multiply everything together. Then you have 2.5 multiplied by 2 multiplied by 10. This brings you 50. And don't forget we have here a negative sign. Then we'll bring it here. So again, we got q enclosed as minus 50. So this is become much easier. Even we have to calculate the three integrals, even we have to calculate the divergence. But since we don't need to look where is the normal surface, it become much easier. Thank you.